Welcome back to this lecture series on pulse width modulation for power electronic converters. So, incidentally today we are getting started off with the last module of this lecture series. This is 40 this is a series of 40 lectures, and these 40 lectures are organized into 13 modules, and today we are going to get started off with the last module, which is on multi-level converter or PWM for multi-level converters. So, the different modules are organized like this. I am just trying to recap so that you can have a quick understanding of what happened when, and if you have not followed all the previous lectures, you can go on and catch up with a particular module and so on and so forth. So, what we started off with is actually overview of power electronic converters. In fact, we started off like how to board connect switches and how not to connect switches, that we have to make sure that an inductive circuit does not get opened out or a capacitance does not get shorted and so on and so forth. So, we found that a DC-DC converter, it is essentially like it is a single pole double throw switch, and we looked at DC-DC converter, we looked at DC-AC converter like voltage source inverters and current source inverters, and we also looked at a multi-level inverter, let us say a neutral point clamped inverter or a flying capacitor inverter or so on and so forth. We discussed the power topologies, the power converter topologies, how are the various switches connected and why they are connected the way they are. That was essentially what we need to do this now. So, for this multi-level converter, if you are going to follow this afresh, you need to basically go to this module and look at some of those lectures which introduce a multi-level converter, particularly a neutral point clamped converter or what is called as a diode clamped converter. So, you may have to look at that and then you have to restart. Of course, I will be picking up the threads from there, and we will have some discussions on that also. And the next module, the second module, is actually on the applications of voltage source converter now. So, we have a lot of voltage source converters, DC AC conversion. We have IGBTs, we have MOSFETs and IGBTs, which are switches which are capable of conducting in both the directions. An IGBT with an anti-parallel diode can conduct in both directions, and it can block voltage of one polarity. Such switches are ideally suited for voltage source converters, and you use a voltage source inverter normally to drive motor drive for variable speed speed drives. That is a very important application. You also use voltage source converter for active PWM or active PWM rectification. You try to rectify at unity power factor, and the ensuring that the rectifier input currents are almost sinusoidal. We will have sinusoidal plus maybe high frequency ripple. So, that PWM rectification is another application of this, and we also have things like static compensation, and many grid connected applications are possible here. Here we briefly reviewed the applications, and we also looked at what kind of load models etc. could be used and so on and so forth now. So, these are actually, this is for the first set of modules. These are more general power electronic course modules. So, here we get particularly into PWM and some basics of PWM generation. So, in this we looked at Fourier series and have harmonic components and symmetries, Y symmetries, Y half wave symmetry, Y quarter wave symmetry, what happens and so on, like in these two modules for example, like half wave symmetry leading to absence of even harmonics and so on and so forth. And in this module we particularly focused on low switching frequency PWM, when you have let us say 2 switching angles in a quarter cycle or 3 switching angles in a quarter cycle and so on. Selective harmonic elimination is one way. So, we looked at selective harmonic elimination. We also briefly discussed offline optimal PWM, and so we tried doing this module for one reason, was like such low frequency PWM are applicable at for high power drives, where the devices cannot switch at high frequency, because every time it turns on and turns off there will be huge amount of energy loss. So, the device cannot go through several switching cycles, and that is one reason. The other reason is more academic or from the learning point of view. It is good to learn these well, and you can grasp several of the fundamentals here, and therefore we go about doing it now. These low frequency PWM which we had done for 2-level inverter are certainly applicable to 3-level inverter. That is one reason I am talking about it now. And these ideas like what we said about half wave symmetry and quarter wave symmetry and things 3-phase symmetry and so on that we discussed here are all equally applicable here also. In the case of 2-level inverter, if you look at the pole voltage, you may have only 2 levels like plus VDC by 2 and minus VDC by 2. Here your pole voltage will be more detailed. It will have plus VDC by 2, 0 and minus VDC by 2. Nevertheless, the same principles are equally applicable. and you can generate low switching frequency. Selective harmonic elimination for multi-level inverter, there have been a lot of work on this, though I am not going to be specifically spending much time discussing this on that. Selective harmonic elimination for multi-level. So, whatever has been discussed for 2 level, the same principles could very well be extended to multi-level now. This is an important module, triangle comparison based PWM. So, particularly sinusoidal PWM and then different kinds of common mode injection now. So, we would look at how to extend this sinusoidal PWM to this case of 3 level inverter. So, that is one important topic that we will anyway take up for discussion, and once you do the sinusoidal PWM, it is also possible for you to add certain common mode and compare them with that is also possible. So, that is also something we can look at. So, the other thing that we need to do is space vector based PWM. So, what we will do first, we need to understand the various voltage vectors produced by 3 level inverter. There is a big difference here now. Earlier in a 2 level inverter, you had a few switching states, there are 3 legs. In 2 level inverter also there are 3 legs, and 3 level inverter also there are 3 legs, because we are talking of DC to 3 phase AC conversion. The number of legs is same. In a 2 level inverter, while there are only 2 complementary switches, in a 3 level inverter there are 4 switches, 2 pairs of complementary switches rather. And in a 3 level inverter, your pole voltage can be plus VDC by 2, 0 or minus VDC by 2. In a 3 level inverter, if you look at the voltage space vectors an inverter can produce, that will be many more than what can be produced by a 2 level inverter. In a 2 level inverter, there are 8 inverter states, 2 multiplied by 2 multiplied by 2. Here there are 27 inverter states, 3 multiplied by 3 multiplied by 3. So, that means there are many voltage space vectors. So, today we would see what are the various voltage space vectors produced also, and we will try and see, like this triangle comparison PWM, when you consider sine triangle PWM for example. And one interesting thing is, it is not unique. When you extend sine triangle PWM from 2 level to 3 level, it is not unique. There are several ways of extending, which actually can lead to different PWM methods, whose waveforms might have different harmonic properties. So, we would like to see the switching sequence for some of them. So, we would look at in terms of the inverter voltage vectors. Most probably in the next lecture, we would look at the space vector based PWM for 3 level inverters in greater detail. So, this second set of course modules, which actually dealt with PWM generation, this is all for 2 level inverter. Once we understand what is a 3 level inverter, and once we understand this, it is possible for us to extend many of these to 3 level inverters. So, then the third set of modules were more about the analytical part in an inverter now. Here the focus is not really on the fundamental voltage. In the earlier case, we learnt how to modulate the inverter so that we get the desired fundamental voltage. Here we are kind of evaluating if there are different PWM methods, if there is a particular PWM method, particular load, how do I calculate the RMS current ripple? If there are 2 different PWM methods, how do I compare the RMS current ripple? The burden of the discussions were actually, that is what was the focus of the discussions. Of course, many of them were not in such detail as could be done in a regular classroom, but I tried providing enough inputs and also give references so that it would be possible for you to do things yourself, and I am hoping that in the assignment sets and all that, they will also, those homework problems might also be of some help to you to understand these concepts better. The third set of modules is more analytical. We look at how much is the current ripple, for example, in the AC side, and we look at what is the DC link current that is flowing on the DC side of the inverter, and this is closely related to the capacitor, because the DC component of the DC link current comes from the DC supply, say the rectifier, and the ripple component of the DC link current, most of it flows through the DC capacitor, and that determines the RMS current through the capacitor, that determines the power loss in the capacitor, that determines the heating in the capacitor and the life of the capacitor, and therefore this DC link current is something very important from the capacitor point of view. So, we tried having a detailed discussion on the DC link current also. Of course, these are all short modules, everything or 2 or 3 lectures each of these modules, but I have tried to give a certain amount of fundamentals, principles which are needed for carrying out these analysis. And one other thing was specifically in the context of motor drive is the pulsating torque. These are all the effects of harmonics. The harmonics cause harmonic currents and therefore a current ripple. The harmonics also cause harmonic fluxes, and the fundamental flux and harmonic current, and again the fundamental current and harmonic flux interact to produce pulsating torque. So, we discussed this pulsating torque for a single, for low switching frequency case and also for the high switching frequency case. So, for the low switching frequency case, we tried to evaluate the 5th, 7th harmonic voltages, etc. We tried to look at the 6th harmonic torque. torque for example, and how you could evaluate specific like harmonic torques like 6, 12 etc. And we also looked at the possibility of eliminating say something like 6th harmonic torque or 12th harmonic torque by appropriately selecting the switching angle. And in the high frequency case where we tried to look at it as the integral of error voltage, we considered the error voltage vector and we tried to integrate that to get the stator flux ripple vector, and we used the q axis component of that to do this job here. Okay. Alright. So, what we are going to do is the evaluation of the inverter loss is the next important thing from a practical point of view, which is what also something that we did now. And this inverter loss is interestingly that the basic ideas of conduction loss and switching loss etc. would actually apply to a 3 level inverter also. So, what we will see is in 2 level inverter, if you are looking at conduction loss, there are only 2 transistors, I mean with anti-parallel diodes. So, for a particular direction of current, it is only this one transistor or other diode, they conduct alternately, and whereas so there is always one device conducting in a leg at any point of time, whereas you find that in a 3 level inverter you will find that 2 devices are conducting at any point of time. So, the loss to that extent, conduction loss is going to be more. On the other hand, the switching loss, whenever an inverter switches, if the inverter is a 2 level inverter, the switch is going to be switching a voltage of VDC, whereas as we will see here, it will be switching only a voltage of VDC by 2, and therefore the switching energy loss could actually be lower. So, there are some reasons that when you go to fairly higher switching frequencies, a 3 level inverter might lead to lower switching loss than the 2 level inverter, or the overall power conversion loss can also be lower than what you can actually get with a 2 level inverter. So, sometimes for power quality kind of applications you could consider doing this, and there are actually comparative studies are also available. I would try to indicate some of these references to you maybe in the next lecture and the last next 2 lectures on this particular topic now. So, we also this in the 4th set of modules we try to look at the inverter dead time and what effect it happens now. Here also you have the same inverter dead time is required. There in a 2 level case you had 2 complementary devices. So, you need a dead time between the 2, the outgoing device is switched off first and the incoming device is switched on later. So, there is a time delay of TD introduced between that. Here in a 3 level inverter you have 2 pairs of complementary devices, and again the outgoing device should be switched off first and then the incoming devices later. Now, with certain amount of thing you can actually do this dead time analysis for here also, but that is something that we are not going to really look at. Again we go in for this went in for this over modulation. This over modulation, what we achieve is from sine triangle PWM, when we go to common mode injection we are able to increase the voltage by 15%. We can again increase like from 0.5 VDC or some 78.5% of 6 step voltage, we come to 90.7% using carry common mode injection alone. From 90.7 to 100% of the 6 step voltage we will need over modulation. That is something that we discussed in the last module. The same philosophy can actually be used with certain modifications to a 3 level inverter also, but in 3 level inverter for a 2 level inverter with over modulation you can increase it from 90.7% to 100%, nearly 10% increase in the voltage is possible through over modulation, whereas that percentage increase could actually be a little lower with this. And of course there are those algorithms that I have mentioned can be expanded, some of them have been extended and some can be extended to over modulation of 3 level inverter. So, if necessary we can also do that. So, but we would be focusing on this. So, this present module is on PWM for multi-level inverter. So, we will take a look at a multi-level inverter and we would look at the pole voltages, the inverter states and the voltage vectors that are being produced by a multi-level inverter. Then we look at sinusoidal PWM for 2 level and how do you extend sinusoidal PWM from 2 level to 3 level inverter, and we will look at some 2-3 interesting possibilities and we will make a comparison of them, and then we will go on to space vector based PWM for multi-level inverter and possibly look at some advanced bus clamping PWM. So, like we had the PWM methods, we had the continuous PWM methods, we had the discontinuous or bus clamping PWM methods for 2 level. We also can have them for the multi-level inverter. So, such things have also been researched. Just like we have the advanced bus clamping PWM methods for the 2 level inverter, it is possible for us to have advanced bus clamping methods for 3 level inverter also. There have been 1 or 2 recent publications in that regard. I would also give an indication to you in that particular direction. Okay. So, now we move on to our this lecture number 38, which is on PWM for 3 level neutral point clamped inverter. This is the first lecture. So, we will have 3 such lectures like this. So, I call this PWM for 3 level neutral point clamped inverter 1. Alright. So, now we have this 2 level voltage source inverter, and as I said before, this thing is a single pole double throw. So, it is a voltage source inverter, the source is a DC voltage and it is an inverter, it is expected to produce AC voltage here now. The loads are expected to be inductive, and therefore, you find that the pole is connected. Every leg is a single pole double throw switch and the pole is connected to one of the load terminals, because it makes sure that the inductive currents do not get opened. There is always a path for the inductive current to flow through. And the DC side is a stiff voltage source. You have a voltage source here and there is capacitance to supply this additional ripple component and so on. So, this is voltage stiff, and the voltage stiff component is coming across the 2 throws. So, there is no possibility of it getting shorted. So, the inductive load does not have a possibility of getting opened out, and this does not have a possibility of getting shorted. That is why the poles, as you might recall, are connected in series with inductive loads, and the throws are connected across voltage stiff elements such as voltage source or capacitors now. So, this is a single pole double throw switch, and again another single pole double throw switch for the Y phase leg and single phase double throw switch for the B phase leg. So, we realize this using a device which can conduct in both directions, but can block with only one polarity, where this is positive with respect to this. You want me to write? I can do this now. This is something which we have already done, whereas the conduction can be in both directions. So, we have such devices, and such devices are used in voltage source inverter. If you are going to the current source inverter, you will need the complementary, you will need the dual of this. A current source inverter would require a switch which can block voltages of 2 polarities, but maybe conduct current in only one direction. Alright. So, this is a voltage source inverter, and it is realized using a single pole double throw switch, as I have shown here. Alright. Now, we need a multi-level converter. What we do is, single pole double throw, there is a pole. Why there is this pole? This is the load terminal is connected here, and you used a single pole double throw, so that you had an capable, you could apply either plus this VDC by 2 measured with respect to O, or minus VDC by 2 measured with respect to O at R. So, your waveform quality can be improved if you can also connect R to the midpoint O. That is one of the ideas now. So, you have an option of either connecting it to the positive bus or this DC midpoint or negative bus. Earlier, the DC midpoint in a 2 level inverter is not available for making an electrical connection. So, here it is available for making an electrical connection, and in fact, sometimes load current may flow into or out of this particular point. Okay. So, you have single pole triple throw switch, and that is what we call as a 3 level inverter. Of course, you can consider single pole 4 throw switch, and that could be called as a 4 level inverter. Again, single pole 5 throw switch, that can be called as a 5 level inverter. Again, you have to be a little careful when you talk about 3 level. Here we say 3 levels because the pole voltage can have 3 different levels, plus VDC by 2, 0 or minus VDC by 2. So, there are some authors who would count the number of levels, let us say in R and Y. If you look at R and Y, you will have 5 different levels, because it can be plus VDC, or it can be plus VDC by 2, or it can be 0, or it can be minus VDC by 2 between the 2, or it can be minus VDC. So, there are 5 different levels. So, sometimes you may find the same thing getting referred as 5 level inverter, but our convention is quite clear. We say the number of levels, we relate it to the number of pole voltages. You look at the pole voltage and the possible levels of number of levels of pole voltages. In the 2 level inverter, there are only 2 of them possible, plus VDC by 2, minus VDC by 2. Here it is plus VDC by 2, 0 and minus VDC by 2, hence we call it 3 level inverter. So, we realize this 3 level inverter, we discussed this one of the lectures, and we spent extensively on how to derive this. And this is what is a single pole triple throw switch realization that we finally came up with. So, if the top 2 devices are on, S1 and S2 are on, the bottom 2 will be off, S3 and S4 will be off, and in that case R will be connected to 0.5 VDC. So, this is a pole getting connected to the top throw. The pole getting connected to the bottom throw is again straightforward to see. What you need to do is keep these 2 off and keep these 2 on, S3 and S4 on. Therefore, what you will get? You will have this pole getting connected to the bottom throw. So, VRO will be now equal to minus 0.5 VDC, earlier it was 0.5 VDC. Now, it is also possible for you to connect R to O. What do? You turn off S1, again you turn off S4, you turn on S2 and S3. So, R could establish a connection with O, and through which path, there are two different paths that would depend on the load current. For example, if the load current is in one direction, the load current could potentially flow like this, or if the load current is in the opposite direction, it can actually flow like this. Let me draw that for your convenience. If the load current is in this direction, for clarity let me draw in this direction, then the load current can actually flow like this from the. On the other hand, if the load current is in the opposite direction, the load current could flow like this. I wanted to draw it in green, so let me maybe I will erase that. Okay. Now let me draw that in green. So if the load current is in the opposite direction, because it is an AC load, so current can be in both the directions, then you will see that it conducts like this. This would be the direction of path. So which transistor and which diode would conduct would actually depend upon the direction of current, but you need to keep both of them on now. So there are three. So in this case, what will happen? R gets connected to O, and you have your VRO is equal to VDC by 2. So this O is sometimes called the neutral, DC neutral, and hence the name neutral point clamped inverter, because you have an ability to apply this there, and you are using these diodes which are called clamping diodes, and so since diodes are being used for connecting this midpoint to this midpoint, sometimes they are also called diode clamped inverter. So these are all the alternate names that you will use now. Sometimes there are also cases where instead of these diodes, active switches are also used. In that case, somebody may call it as active clamped 3-level inverter, but that is something we are not looking at now. So this is called neutral point clamped inverter, or diode clamped inverter, or 3-level inverter. These are the different names now. So if you can see this way, we have a capability of this. There is a voltage source, and this is the pole, and there are 3 different throw voltages, and this converter has an ability to apply the the throw voltage, any desired throw voltage at the pole, irrespective of the direction of current. That is an attribute of voltage source converters. Let us say the current is like this. Now you want this voltage to be applied, you turn on these two. So your current conduction will be like this through the transistors, and it will go along like this. Now if the current conduction is in the opposite direction, then it would go like this and go back there. So it is possible for you to conduct like this. Maybe I can draw that. So for example, the conduction can be like this. In the other direction, the current conduction could be like this. So this converter has an ability to apply either 0.5 VDC or 0 or minus 0.5 VDC at the pole, regardless of the direction of the current at the pole. It can apply any of the throw voltages at the pole now. The same way it is at the bottom thing also now. So let us just summarize the whole operation in terms of a table. So you have S1, you have S2, you have S3, you have S4, and you have the pole voltage VRO. Okay. So now if S1 is on and S2 is also on, S3 and S4 are off, you get 0.5 VDC. You get 0.5 VDC. This is the voltage now. Again, if you have S1 is off, S4 is also off, S2 and S3 are on, then you get VRO is equal to 0. So that is getting connected to that. So this is where the pole voltage pole is getting connected to the DC bus midpoint. Again you have another possibility. You have S1 and S2 are off and S3 and S4 are on. In this case, you are applying minus 0.5 VDC at the pole, measured with respect to this point O. So you have these possibilities now. So you do not consider one of those possibilities. What is that possibility? Keeping S2 and S3 off, S2 and S3 off and S1 and S4 on, because that means S2 and S3 are off means it is totally open, the load is open, which is not something that you want to do. So you have this kind of possibility here. So what can you identify here? You look at S1, and whatever is your S1, S3 is complementary to that. If S1 is high, S3 is low. If S1 is low, S3 is high. The same way you can see S2 and you can see S4, they are also complementary with one another. Therefore, you can say that S1 and S3 are complementary and S2 and S4 complementary. This is the reason I told you that in a 2 level inverter you have one pair of complementary switches, here you have 2 pairs of complementary switches now. So, there it is suffice for you to generate one gating signal and the other gating signal would come by taking its complement. Here you have to generate 2 gating signals, maybe for S1 and S2, and S3 would come by complementing S1 and S4 would come by complementing S2. So, you need to produce 2 gating signals and that is going to significantly change. So, earlier in sine triangle PWM for 2 level inverter you could compare one sine wave with one triangle. Now, you cannot have one sine wave with one triangle because you have to produce 2 signals. So, it has to be like one sine wave with two carriers, which is what we look at, and sometimes it can also be with 2 sine waves with one carrier. Okay. So, this is something that we will look at here. So, S1 and S2, and so you need this kind of a logic. So, we need to generate S1 and S2 for example, and S3 and S4 can be generated as complements of S1 and S2 respectively. Okay. So, if you look at the instantaneous pole voltages just we have been discussing, it can be 0. When would it be 0? So, when both when the pole R is connected to O by the middle 2 switches being on, then VRO is equal to 0. The same way Vy can be 0 if the middle 2 switches in the Y phase leg are on. Again, if the middle 2 switches in the B phase are on and the extreme 2 are off, you get VBO is equal to 0. So, this is something different from the 2 level inverter, and this plus or minus VDC by 2 is similar to what you had in a 2 level inverter, except that you have to keep both S1 and S2 on and S3 and S4 off for plus VDC by 2. For this minus VDC by 2 you must have S3 and S4 both on. So, there will be 2 switches will be connecting, it could be 2 transistors or the 2 anti-parallel diodes that could be connecting when you are really doing this now. The instantaneous pole voltages are 0 plus or minus VDC by 2, 0 plus or minus VDC by 2 and so on. So, when I write VDC by 2 you can inherently see that I am ignoring the device drops just as we have been doing all through. Okay. Now, VRY is what is VRY? The same kind of equation as before, VRO minus VYO. And what is VRN? 1/3 of VRY minus VBR, assuming the load to be star connected balanced load, the neutral is not connected anywhere else. This is the kind of star connected balanced load you assume here as before. So, the main difference that comes is in this value 0, otherwise it is similar to that of 2 level inverter. So, the analysis procedure from pole voltage you going to line and the line to neutral voltage on the load, they are pretty similar now. So, now you have VRO, VYO, VBO, and they can, from that you can get VRY, VYB and VBR, and you can also get VRN, VYN and VBN, and VRN, VYN and VBN can be used to obtain V alpha and V beta. The same space vector transformation is valid because VRN plus VYN plus VBN is equal to 0. Under this condition you have V alpha is equal to 3 by 2 VRN as before, and V beta is equal to root 3 by 2 times VYN minus VBN. The only difference would be in the possible values of VRN. Earlier in a 2 level inverter, what are the various values of VRN possible? The various values of VRN possible would be 0 plus or minus VDC by 3 plus or minus 2 VDC by 3, whereas more number of values would be possible here. For example, you may be able to look at plus or minus VDC by 6 and so on and so forth. So, you will have more number of values because VRO you have one additional value. So, VRY you will have more additional. So, you have 3 possible values against 2 in case of 2 level inverter. So, VRY you would have 5 different values, it can be plus VDC by 2, let me just write it down here. So, VRY would be able to take values like plus VDC, and it will also be able to take minus VDC, right, because if VRO is minus VDC by 2 and VYO is equal to plus VDC by 2, and VRY can also take the values of plus or minus VDC by 2, and it can also take the values of 0. So, there are 5 levels. This is why I said that sometimes authors may call this as a 5 level inverter because VRY has 5 possible values now. Again, next if you are trying to do VRN is equal to 1 by 3 times of VRY minus VBR. So, you have different possibilities. If you substitute one after the other, you would be able to get many different possibilities. So, what are the different possibilities? So, VRY itself has 5 possibilities, VBR itself has 5 possibilities. So, let us look at some possibility. If let us say VRY is equal to plus VDC and VBR is equal to minus VDC, in that case what you will have is you will have 2 VDC by 3, This is similar to what we had in a 2 level inverter. So, let me write down one possible value is 2 VDC by 3 as in the case of a 2 level inverter. Again it can be plus or minus, if VRY can be minus VDC and VBR can be plus VDC. So, you can have plus or minus VDC by 3 as you had in a 2 level inverter. Now, let me say VRY is equal to plus VDC, whereas VRY is equal to minus VDC by 2. So, in that case what you will have, this is VDC and this is minus of minus VDC by 2 will be 3 VDC by 2. So, that will be only equal to VDC by 2. I hope I am not making any mistake. This is VDC and minus of minus VDC by 2 is 3 VDC by 2. So, you will have VDC by 2 as your VRN. So, it is also possible that you can get VDC by 2 as a possible value and it can be plus or minus VDC by 2. So, you can also look at plus or minus VDC by 3. So, you would also be able to look at plus or minus VDC by 6 and you will also be able to get 0. So, if you look at this, interestingly what you will get here is, if you need 2 VDC by 3, that is possible with only one possibility, that is VRY has to be VDC and VBR has to be minus VDC, otherwise this is not possible, 2 VDC by 3 is not possible. But if you look at VDC by 2, then you can look at a possibility of this being plus VDC and this being minus VDC by 2, or you can also look at the possibility of this being VDC by 2 and this being minus VDC. So, you have multiple possibilities that lead to here now, and if you look at the possibility of VDC by 3, you will see that there are more number of possibilities which will give you VDC by 3 and even more number of possibilities for VDC by 6, and finally for 0 you have more possibilities, in the sense both can be VDC, that is one possibility, both can be VDC by 2, that is another possibility second, and both can be 0, that is third possibility, both can be minus VDC by 2, that would be the fourth possibility, both can be minus VDC, that would be the fifth possibility. You have 5 different possibilities. So, the highest possible line to line voltage, there is a unique possibility, and when you go to slightly lower line to line voltage, you have more possibilities. As you go to lower and lower voltages, you get more and more possibilities, and 0 is where you have the highest possibility, and this is a 3 level inverter. You go to 5 level inverter or 7 level inverter, you have many such possible states and many possible states which will give you the same voltage, and these that is what is interesting. So, there are 2 different inverter states which can possibly give you the same line voltage, and multiple inverter states can give you that. That is what gives us the leeway to design more and more PWM methods. As far as the load is concerned, it is going to look at what is the voltage. So, if it is 0, the load does not care if this 0 has been achieved by keeping all the 3 poles at plus VDC by 2 or minus VDC by 2 or all 3 poles at 0. Again, if the if VRY may be plus VDC by 6, it can be VR may be at some level, Y phase can be at some level, B phase can be some level, but VRY can be plus VDC by 6 and VYB can be minus VDC by 6 and VBR can be 0, for example. So, there are many possibilities, that is multiple inverter states lead to the same set of 3 phase output voltages. We need a particular output voltage, that is what the load cares, but that is possible to generate using multiple sets of inverter states, particularly when you are talking of voltages which are low in amplitude, so not close to VDC. So, this is what allows us to design many PWM methods now. So, now if we have VRN available, you can also do this. So, VRN and you have VYN and VBN values, they can be transformed into space vector domain. 3 by 2 times VRN is your V alpha, and Vyn minus Vbn into root 3 by 2 is V beta. So, as you know what we did this is the R, Y and B axis, and this is the 3 phase axis, and these are the 2 phase orthogonal axis in the stationary reference frame alpha beta. We call them alpha and beta, and again there are different authors might use different conventions. You basically have your V alpha as Vn cos 0 plus Vyn cos 120 plus Vbn cos 240, and that becomes 3 by 2 times Vrn when you have this condition Vrn plus Vyn plus Vbn is equal to 0. And then you have this V beta is essentially Vrn sin 0 which is 0 and Vyn sin 120 which is same as Vyn cos 30 plus Vbn sin 240 which is same as Vbn cos 150, and this becomes root 3 by 2 times Vyn minus Vbn. So, once you have Vrn, Vyn and Vbn, it is possible to calculate V alpha and V beta, and these are the components of the vector. So, you can say V alpha square plus V beta square under root, that will give you the magnitude of the vector. Tan inverse of V beta upon V alpha will give you the angle of the vector now. So, it is possible for you to calculate many of the inverter states. This is what we did for a 2 level case also. In the 2 level case they are very clear, all the top switches are on is plus plus plus. So, here you will see all the 3 line to line voltages are 0, all the 3 line to neutral voltages VRN, VY and VBN are also 0, and you will get your V alpha to be 0, V beta equal to 0. The same story when you use minus minus minus, that is all the 3 bottom are off, whereas if you use plus minus minus like here, you will see that you would have got, excuse me, so if you use for example plus minus minus, you will see that your VRN is 2 VDC by 3, this is a 2 level inverter, and VYN equals VBN equals minus VDC by 3, and this VRN, VYN and VBN will give you V alpha is equal to VDC and V beta is equal to 0, and that is what is this vector, that is what is this vector. Now, let us say I am looking at this inverter state, here VRO is minus VDC by 2, VYO is plus VDC by 2 and VBO is equal to minus VDC by 2. On the other hand, if I look at VRN, I will find that VRN is minus VDC by 3, VYN is 2 VDC by 3 and VBN is equal to minus VDC by 3. So, the 3 will sum up to 0, VRO plus VYO plus VBO will not sum up to 0, whereas VRN plus VYN plus VBN will sum up to 0. So, this is what you will have. So, minus minus minus, you add all this and you get this. So, this is one vector. So, this will actually give you V alpha is equal to minus 0.5 VDC and V beta is equal to root 3 by 2 VDC, you get this now. You can do a similar analysis for all these and you get these active vectors. You will always find that they have a magnitude equal to, the active vectors will have a magnitude equal to VDC. This is according to our conventions. The way we have defined V alpha and V beta here, you go by that, you get magnitude VDC. This is also of magnitude VDC and this angle is 60 degree. So, this is what we did in a 2 level inverter. So, the same transformation, but different sets of 3 phase pole voltages, that is all that matters now. The different 3 pole voltages will give you 2 different sets of line to line voltages and different sets of line to neutral voltages, and therefore, different sets of voltage vectors in a 3 level inverter, which is what we are going to see now. So, the 3 level inverter, you have particular cases. So, like for example, you take the first case, that is R phase top is connected to the top throw, that is the top 2 switches are on, Y phase the bottom 2 switches are on and the B phase also bottom 2 switches are on. So, here you have VRO is equal to plus VDC by 2, VYO is equal to minus VDC by 2 and VBO is equal to minus VDC by 2. This is same as what you had in a 2 level inverter. So, the inverter state is, we call it as plus minus minus and the vector is the same thing, it will be VDC. So, this is your alpha axis and this is your beta axis. Maybe it may be good for me to indicate alpha axis and beta axis. This is what is our alpha axis and this is our beta axis. So, you have the same thing of your V alpha is equal to VDC and V beta is equal to 0 for this case. So, you have this vector as we have drawn here now. Again, all these states that I have shown here are common to 2 level inverter and the 3 level inverter. This means R phase top 2 devices are on, Y phase top 2 devices are on, B phase bottom 2 are on and the pole voltages are plus VDC by 2, plus VDC by 2, minus VDC by 2, which is possible for a 2 level inverter also, in case of 2 level inverter also, and the vector is the same, the angle is the magnitude is VDC and angle is 60 degrees here. Again, this minus plus minus is something which is common, because you know this is again what you have with the 2 level inverter. So, again 4, 5 and 6, these are similar to what we had in a 2 level inverter. So, there are how many inverter states are there now? There are 3 possibilities. For example, R phase may be positive plus VDC by 2, or it may be connected to the DC midpoint 0, or it can be connected to the negative bus minus. So, there are 3 possibilities. Y phase has 3 possibilities, B phase has 3 possibilities, it is 3 multiplied by 3 multiplied by 3. There are 27 states. Out of 27 states, we have accounted for only 6 states. Now, if you look at for other states, for example, let us say we have a state minus minus minus. So, what does it mean? In all the 3 legs, the bottom 2 devices are on. So, that means the line to line voltages are 0, the line to neutral voltages on the load are 0, therefore, V alpha V beta are 0. I am showing it by a circle. I mean, this is a null vector. The same situation is obtained even when you do 0 0 0. all the 3 phase poles are connected to the DC midpoint. The middle 2 switches are kept on in all these cases now. Again you connect it as plus plus plus, that is the top 2 switches are on in both the in all the 3 legs now. So, all of them will lead to this now. So, now you see a small difference. Earlier it was only minus 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 and plus 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 were available in a 2 level inverter, and these were called the 0 states, which you call as 0 and 7. We designated them as 0 and 7, minus 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 and plus plus plus. Here all bottom devices are on, here all the top devices are on. So, here you have all the bottom 2 devices are on, all the top 2 devices are on, all the middle 2 devices are on. So, you have these 3 0 states now. So, we have accounted for 6 plus 3 9, there are still 18 more states are remaining now. So, what are those states now? See, for example, let us say here it is all connected between plus and minus. All these states, though you can connect it to 0, in these 6 states you find that the inverter leg is connected either to positive or to negative, and not all of them positive, not all of them negative, that is what you find. So, let us say we look at only those combinations where the inverter leg is either connected to positive or to 0, that is again possible, no? So, in that case what happens is the inverter, the 3 level inverter reduces to something like a 2 level inverter whose DC bus voltage is VDC by 2, alright. So, let me just write that down now. Okay. So, I am looking at plus 0 0. So, what happens with plus 0 0? I am going to get an inverter state like this, plus 0 0. This magnitude will be VDC by 2. Why? Because this is very similar to the case of a 3 level inverter, I mean the 2 level inverter, except that the DC voltage now is VDC by 2. So, the line to line voltages here are minus VDC 0, I mean VDC 0 and minus VDC, here it is VDC by 2 0 and minus VDC by 2, that is all. So, you will have half of this now. Again you can use that again, that is you look at combinations where they are connected only between plus and 0. So, you get the other combination. So, if you have plus plus 0, here you may have minus plus 0, that will lead to a vector like this. Again you will have not mine, I am sorry, did I say, yeah, this is 0 plus 0, and here I have 0 plus plus, and here I can think of 0 0 plus, and here I can think of the state plus 0 plus. So, these are 6 inverter states where the legs are connected, the midpoints are connected either to plus or 0. So, these are like similar to active states in a 2 level inverter, but whose DC bus voltage is VDC by 2, and so all these produce voltage vectors of length equal to VDC by 2, and their angles are 60 degrees as before. Now, if we have plus 0 0, what is R phase is VDC by 2, Y phase is 0, B phase is also 0, the pole voltages are 0. You can what is the line to line voltage? It is plus VDC by 2, VRY is plus VDC by 2, VYB is 0, VBR is minus VDC by 2. You can achieve the same thing if, for example, you use 0 minus minus. So, here again VRY will be plus VDC by 2, VYB will be 0 and VBR will be minus VDC by 2. So, they will result in the same set of 3 phase line to line voltages, and therefore, the 3 phase line to neutral voltages on the load, again therefore, the same voltage vector. Again I can look at the same, I can look at 0 0 minus, this leads to the same set of pole voltages, this also leads to the same vector. Again I would have the inverter state minus 0 minus leading to the same vector. I will have minus 0 0, here I can have minus minus 0, here I can think of 0 minus 0. So, these are another 6 more vectors. So, these are combinations, the where I have drawn in the red ink, these are all combinations of 0 and minus. It is like I am having the 3 level inverter, but I am switching only between minus and 0. So, some legs may be connected to 0, some other the remaining legs will be connected to minus. So, these would be the active vectors. So, now how many have we been able to account for? We have been able to account for first the 6 outer vectors, and then these 3 9, and then now 12 of them. So, about 21 of them we have accounted for. Now, how many inverter states are remaining? 6 inverter states are remaining. What are the inverter states remaining? The kind of inverter states remaining are of this nature, like plus 0 minus. This is what we have not considered till now, or something like 0 plus minus, or minus 0 plus, and so on. So, what do these things stand for? They actually, one of them has plus VDC by 2, another one would have minus VDC by 2, the third one would have 0. Those you have 6 combinations will be available. So, if you take the first phase, it can be either plus VDC by 2, 0, or minus VDC by 2. So, the second phase can have 2 possibilities and third will have 1 possibility. So, you have 6 such states now. So, the question is where will be the vectors now. So, if you look at plus 0 minus, VRY is equal to VDC by 2, and sorry, VYB is equal to minus VDC by 2, and VBR is equal to minus VDC. So, this is VDC by 2, VDC by 2, this is minus VDC. From here you can calculate VR and VY and VB and V alpha, V beta, and you can come up to that. So, there is no issues, you can actually do it. But what you will find here is, you see here plus minus minus, and you see here plus plus minus, and when you go for plus 0 minus, this will actually be midway between the two. It will be symmetric from this, and what you will find here is that actually it will go like here. This would be the vector produced by plus 0 minus. Again, this will be the vector produced by, here the transition is from plus to minus. So, you look at 0 plus minus. Again here if you look at this, this will be minus 0 plus, and that would produce a vector like this, and I missed something here. So, it will be minus plus 0, and that would be producing a vector like this. Then if you look at here, this will be 0 minus plus like this now, and then you look at here, this the other fellow will be producing here, this is plus minus 0. So, you can see some interesting observations here. Now, there is this 0 state. How many active vectors are here? Actually 27 inverter states are there. These 6 states leads to 6 vectors, they lead to 6 vectors are all of magnitude VDC by 2. Then there are 12 different inverter states which lead to 6 distinct active vectors of VDC by 2. So, 2 of them produce the same vector. Now, then you have 3 of them producing the same vector, the null vectors. There are 3 0 states, they produce that, and then there are these 6 active vectors which produce, I mean active states producing 6 active vectors. So, whatever tip is found on the outer hexagon, they correspond to 12 different inverter states, and they produce 12 active vectors, and that is what you find them there. And the inner one, there are 12 of them producing 6 active vectors totally, and the innermost are 3 inverter states producing a single active vector. So, if you count the number of distinct active voltage vectors or voltage vectors, you have 12 plus 6 plus 1. There are 19 distinct voltage vectors produced by 27 inverter states. You see that there are lots of possibilities. In the case of a 2 level inverter, you had only one possibility. This vector can be applied either using this state or that state, and that itself led to many PWM methods, and that is the main reason why you had the bus clamping PWM method. The common mode addition is mainly because of this, and we further invented that, like looked at, learned that the active state can be applied more than once and so on, or active state 2 can be applied more than once, and that led us to the advanced bus clamping PWM method. Now, if you look at, there are so many possibilities. This can be applied through 3 different inverter states, and all these vectors can actually applied by using 2 different inverter states. So, a 3 level inverter gives you much more degrees of freedom, much more, lot more opportunities to explore and design new PWM methods than even a 2 level inverter does. And we had, with a 2 level inverter, we could discuss the PWM methods for about 20-25 lectures. You can see that we can discuss about PWM methods probably for 50 lectures, but that is not what we are going to do, because the fundamental principles are many times common. Once you understand the fundamental principles for PWM for 2 level inverter, and then you understand what is a 3 level inverter, then you should be able to design reasonably good PWM methods for a 3 level inverter, and therefore we will be restricting it only to 3 lectures here. Alright. So, but you should realize that it gives a lot of exciting possibilities. There are so many possibilities of doing things now. Okay. Now, let me just give another more indication. You will need a vector, for example. So, let me say, let me take this triangle. It is better that I choose yet another color. Would this be alright? Okay. So, let us say I have this triangular region. I have a tip falling here. I have a reference vector whose tip falls here. So, now what happens is I can use the 3 nearest vectors. This is what we are actually heading towards. Why does it give you better waveform quality? If you need to produce this vector using a 2 level inverter, you have to use this null vector, you have to use this active vector and use this active vector. Obviously, you will be using active vector 2 for the longest duration, followed by active vector 1 and then the null vector to produce this one. So, whenever you are applying, you are never getting to apply this, you are applying here, here and here, and the error is very high, particularly when you are applying active vector 1, the error between the desired vector and the actual vector is so long. Again, when you are applying null vector, the delay is so long. Now, since you have many more possibilities, what you can do, you apply the 3 closest vectors. So, you see that the error is so small, here also the error is so small. So, this error voltage vector is nothing but the harmonics, you have the ripple voltages in all the 3 phases. If you transform the ripples in all the 3 phases into the space vector domain, that becomes your error vector. Again this error vector, that gives your instantaneous error vector. Now, your instantaneous error vector is low and therefore its integral, the instantaneous stator flux ripple or the instantaneous current ripple is going to be low, and that is the reason why a 3 level inverter gives you, main reason gives you better waveform quality than that one. Now, again you see that there are multiple possibilities. For example, there are 2 different inverter states which you can use to apply this, and that will give you a lot of opportunities to design PWM methods now. So, if you look at, now we have looked at just the switches, we have looked at the possibilities of pole voltages and so on. Now, we would look at the average voltages. If you were looking at DC chopper, what you are trying to see is you want to apply certain average voltage here, you would want that same average voltage applied at the pole. Now, this is pole, average pole voltage. So, at the pole sometimes it is V in and sometimes 0, and what you do is you get certain average voltage. This average voltage will be constant against time, because that is what you want in a DC chopper. So, this switches you will make sure that they normally power flows in one direction. If this is a regenerative load like a DC machine, you could actually make these switches conduct in both the directions, and you can make this a regenerative chopper. So, you can make it a 2 quadrant chopper also. Now, what do you do? How do you produce the PWM signals is by comparing this carrier with a modulating signal as we did before, and the duty ratios are constant now. What we need in case of a 3 phase inverter is, we would need this VRO average, this pole voltage, the average pole voltage now needs to be varied sinusoidally. We want to vary VRO average sinusoidally, VYO average sinusoidally and VBO average sinusoidally, such that we will get VRO average as a sinusoid, VYB as a sinusoid and VBR as a sinusoid, and all these 3 sinusoids will be balanced symmetric. So, if you want to produce VRO average, if you use a 2 level inverter, we want this alternating. So, sometimes it will be positive, sometimes it will be negative. If you want your VRO average something like 0.25 VDC, in a 2 level inverter you could do this by connecting it to 0.5 VDC for most of the time and minus 0.5 VDC for a shorter duration of time. Whereas, if you want to do it with a 3 level inverter, you do not have to use minus 0.5 VDC at all, and this is 0.5 VDC and 0. So, you will get that 50% of the time you apply 0.5 VDC, 50% you apply 0, you will get 0.25 VDC. So, what happens now, you are able to generate the same average voltage, but the instantaneous error is small. Here the instantaneous error, as I pointed out even in the lectures on multi-level inverter, is so high, whereas here the instantaneous error is so small. So, the worst case instantaneous error is reduced, and obviously the flux thing is going to be reduced now. It is this reduction in the error in pole voltage is what got reflected as the reduction in the voltage error vector in the space vector domain. Alright. So, you can use like this. So, what we want to do is we actually want to vary this VRO average sinusoidally and VYO average to be another sinusoid at the same amplitude, same frequency 120 degree later, and VYO average also as another sinusoid. So, if you do this like that, VRO average are all sinusoids, they are all same amplitude, same frequency 120 degree phase shifted, then you will get your VYRY average like this and VYB average like this, and this I am sorry is VBR average. So, this is VBR average. So, you will get the 3 phase line to line voltages like that. So, the same idea that you used in the sinusoidal PWM we can use here for 2 level inverter. You can use 3 phase sinusoidal signals. The only trouble is you cannot have single carrier, as we will just soon see now. So, they are like MR, MY, MB, and the VRO average is MR by VP times VDC by 2. So, we are not going into over modulation. So, MR and VRO are just have the same wave shape, just scaled versions, VRY average, VRN average, and we know all this, we have done this enough number of times before. So, you can achieve what you want. You can also add common mode like we did in 2 level inverter, nothing stops us by from adding this MCM to MR MY MB to get your MR star MY star MB star, and you try to produce VRO average which is a scaled version of MR star. You produce VYO average which is a scaled version of MY star. How you do it, that is what we have to see. You need to compare them with triangle, what kind of triangle you have to see now. But you can, it is possible for you to produce. Once you produce like this, you have your VRY average is VRO average minus VYO average, and VRN average is like this, same as what it was in a 2 level inverter, and all these are very similar now. So, once you have VRN average, VYN average and VBN average, you can always transform them into V alpha average and V beta average, our standard space vector transformation. Of course, here the VRN average plus VYN average plus VBN average is equal to 0 is still valid now. So, in the difference comes in the triangle. For example, in the case of 2 level inverter, there is one modulating signal and one triangle, and there are other modulating signals YB as well compared against the same triangle now, but the single triangle carrier won't suffice for you. So, what you do now is basically you have 2 different carriers is one way of doing it. One way of doing it is you have the same RYB, but now have level shifted carriers. So, you see that it goes between 0 and 1 and this goes between minus 1 and 0. So, they have 2 level shifted carriers now, and this comparison can give you some switching and this comparison can give you some other switching now. For example, your logic could be you take R phase here, it is greater than both the carriers, then you can say R phase both the top devices will be on. Now, here you let us say take some other case, you take the R phase here. Now, R phase is lower than this carrier, but higher than this carrier. So, you can say for R phase the middle 2 switches will be on, and now you take R phase here, it is lower than both the carriers, here you can say that both the bottom devices will be on. So, this could be the switching logic by which you can come up and produce PWM waveforms. So, this can be done using 2 level shifted carriers. This is one good way of extending sine triangle PWM for 2 level to 3 level. And it actually the harmonic distortion is also pretty good with this, as we will see compared to other things now. So, as I just mentioned that you compare them with carrier and obviously these are high frequency carriers, and let me use a different color here. Yeah. So, these are high frequency carriers, though I have shown the carrier to be a low frequency for purpose of illustration. What I can also do is I can also have this phase shifted like this. I can also have the carrier phase shifted, no problem, it will still work. The fundamental voltage I will still get. So, the 2 carriers are phase shifted from each other. So, what would be the effect of doing this now? So, you see that this is at some phase, this is at some other phase, maybe phase shifted by 20 degree or 30 degree at the carrier frequency. This will not affect the fundamental, but this will impact the harmonics. So, sometimes the harmonics may change for better and many times it may change for worse. One particular case of phase shifting is have the 2 carriers out of phase. What I actually have is this is the original top carrier and this is the bottom carrier, the 2 are actually out of phase. From the picture you may not, I could have plotted probably using 2 different colors, this black and this brown, you would have known that. So, this is top carrier and this is bottom carrier. So, you can do this now. So, what you will see here is there is yet another, before we go into that, you need 2 carriers. So, there are lots of studies have been done. There is also some places where they have used 2 modulating signals and a single carrier, that is also there in the literature. I could give you the reference probably in the next lecture. Now, if you want to do this, you see that there is no intersection between this and this. Again, in this part, this carrier and there is no intersection. So, what you can actually do is, let us say you shift this fellow up, you shift this fellow up. What is this? The R phase I have just shifted up. So, the R phase signal is like this. Now, I can actually compare. So, this should be at 0 crossing. So, what I can do is I can ignore totally the lower part, I can ignore this part, I can ignore this part. I can have a level shifted thing which is like this, and this part the sign is level shifted, and you can see that the instance of comparisons all will not change if I do it properly. I have not drawn it very clearly. So, you can use it using a single carrier PWM also, and you will see that when you can analyze the switching sequence, which we will do it in the next class, the switching sequence with for out of phase carrier and the switching sequence for in phase carrier would be actually different, and you will find that the in phase carrier is better in terms of the voltage error vector, it will lead to lower voltage vector. I would leave this as a home exercise for you. I will come back and anyway do it in the next lecture. So, next lecture we can get started off from this point, and I thank you very much for your interest and your patience, and I look forward to your continued participation in the next 2 lectures. Thank you very much.